Okay, another section on kinetics. We're going to talk about integrated rate laws, and I'll ask you to actually do the calculus, which, based on all the calculus you've done in quantum mechanics, I think you'll find it very easy. So the key idea is that the composition of reaction mixture can be predicted by integrating a rate law. So we know that rate is a derivative. So if you want to think about how things change over a finite period of time rather than infinitesimal, you have to integrate it. And so we'll just do that and see where the equations came from that you used in Chem 108. So there are two principal uses, which is an important thing to think about at the bottom of the page here. One's just to predict the concentration of a species at any time after you start the reaction, so see how concentration changes with time. And the other is to figure out the order of the reaction. So when we look at the equations we get, we'll be able to see what should be a straight line when we graph it, and therefore what order the reaction should be. So I am just going to jump, these are all just justifications for the different orders of the reactions, zeroth, first, second. And so let's look at zeroth order. So for a zeroth order reaction, which is often happens when you have like a reaction in water that water reacts. And then what you'll see is it appears like it doesn't depend on the concentration of water because it's not changing and it's so large. And so the rate just ends up being a constant. And so the first thing you have to do is think about if rate's equal to a constant and rate equals a derivative, then in order to integrate it, we have to separate the variables. So we'll take the t over to this side and integrate over t, and keep the a on this side and integrate over a concentration change. So I'm going to stop this share. I'm going to share Mathematica. New. Okay, now I have to share that. So you know how to do this because you've done it so much. I'm just going to do it using the palette, just because it's more visual. So I'm integrating the left-hand side from A0 up to A at some t. And the function I'm integrating is just 1, because it's first order. So it's 1 times dA. And so when you do that integral, you get negative A0 plus AT. And so keep note of that. I'm going to go back. So negative A0. So really what you get is the concentration at some time minus the initial concentration. So same exact thing that I have here. And on the right-hand side, it's always going to be the same integral. Constant times dt gives you delta t. And if you set your watch and say the time I started is time 0, then that's just the time you ended at. So this is the integrated rate law for a first order reaction, or for a zeroth order, I'm sorry. For a first order, we know that the rate depends on a to the first power. So we'll do the exact same thing. We'll look at our derivative. We'll pull the dt over to the right-hand side. So we have the t's on this side and the concentration over here with its differential. So now we're integrating dx over x, essentially, changing concentration of A over the concentration of A. And plug that into Mathematica, and you get natural log of A at some time minus the natural log of the concentration you started with. And then the right-hand side's the same thing, negative KT. For a second order, you have to think about the different possibilities with a second order. What you saw in Chem 108 was a second order, where it's second order with respect to one species. So the rate equals negative K A squared. And that's just the same as what we've been doing. Take the A squared over here, keep the T over here. The right-hand side comes the same thing. And what you get on this side is, let's just plug that into Mathematica, show you where that comes from. So we're going to integrate, same range, so A0, A at some new time, and we're integrating the function 1 divided by A squared, and we're integrating over A. Really? It's kind of odd, like any time at all. So you end up, because of the negative that comes out, because the squared is in the denominator, with the reverse. You have 1 over this concentration you started with, minus 1 over the concentration at some time. So if you look at how that, then you can rearrange it. So it was 1 over A0 minus 1 over AT. You can just pull the negative KT over to this side, and the 1 over A at some new time to that side. And that's your integrated rate law for second order when they're both the same species. It's a little more challenging if you have second order. So this is one you didn't see in Gen Chem, where it's first order with respect to 2 different species. So now when we pull the concentrations over to this side, we have 2 different things to integrate over, and you can't do that. So you have to use the stoichiometry and see how the concentrations compare to each other. So if they each have a 1 out front, then concentration of A is going to be what it started with minus X, and the concentration of B will be what it started with minus X. So if there was like a 2 here, then this would be B0 minus 2X. So the stoichiometry allows you to set up an equation where you only have one thing changing. A0 and B0 are constants. So we can, rather than integrate over A, we can integrate over X. The only thing you have to realize is that if A changes with X, -1, that means dA, you take the dx to this side, equals negative dx. So we just have to change the sign when we integrate this, but now we can integrate dx dt. So if I write dx dt, take the dt to the right-hand side like we've done every single time, integrate that. And now there's a negative sign here, so those are going to cancel. And I have now dx instead of dA, but I'm integrating over the change in the concentrations from 0 to some new concentration. And let me just see. Oh, there it is, sorry. I just did this a little bit earlier. So I plugged it in with the palette, and I have the product of A0 minus X times B0 minus X raised to the -1. I'm integrating over X. And what you come up with needs to be simplified a little bit in order to look like what they have in the book. But it's fairly easy to rearrange that knowing your log relationships. So all of your log relationships where log of x plus log of y equals log of xy, etc. Then you can group them all together and you get this expression right here, which is a little bit not useful because it's not in terms of how the concentration at some future time, what it would look like if you knew the original concentrations. So use this to derive equation 4a. 4a just solves for a at some new time, which we defined as a0 minus x, so you plug it in right here. And they also solve for B at some future time, which you plug in here. To get it out of the natural log, you have to take E, raise it to both sides, and then you'll be able to derive the function that they have, and they actually go through it in a justification that shows you how the concentration changes with time, so you could use it just like we use the other integrated rate laws. So this goes through exactly what I just did. Ending right up here with the equation I got from Mathematica, and then going ahead and starting to rearrange that and solve for the individual AT and BT. So the only other thing I want you to do now, the rest of this topic just focuses on half-lives. And so if you look at each of these, let's just look at a first order reaction to remind yourself how you do this. First order reaction, it was natural log of A at some time minus natural log of A0. So you can make that into the log of a ratio. And half-life is just the time at which the concentration is 1/2 of what you started with. So that means AT equals 1/2 of A0. So I can plug that in here. And then those will cancel. And the negative, it's also true that negative of natural log of 1/x equals natural log of x. So if I cancel that negative, I change this into natural log of 2 equals kt 1/2, or natural log of 2 over k equals t 1/2 for first order. So you should take a few minutes and derive the half-life for 0th order and 2nd order with the same species. I think it'd be very hard to do it the 2nd order with respect to different species. And that is the entire topic. So we have 3 topics left. If I get through them, who knows, we may cancel one just because we can, but we'll see.